Hello and welcome. This video is all about synchronous counters. In this video, we'll be creating a synchronous counter, particularly a 3-bit synchronous counter. And specifically for this video, I will concentrate on making this synchronous counter using T flip-flops. Now, in the previous 3 videos, we've talked about a T flip-flop. We developed a test bench for a T flip-flop, and then we designed a ripple counter, a 3-bit ripple counter using the T flip-flop. We made it an up counter. We also made it a down counter. In this video, we'll focus on an up counter, a 3-bit synchronous up counter, and again, we'll make use of the T flip-flop. So let's go ahead and design the counter. So to do so, what we're going to do is start by our truth table like we do in many scenarios. We're interested in a 3-bit up counter. In other words, a 3-bit up counter we know typically runs from 000 to 001 to 010 to 011 to 100, 101, 110, and then 111. And after this, it cycles back to 000. Let's give this some output. Since I'm going to use T flip-flops, I'll use Q to represent the output. So let's say Q2, Q1, Q0. Now, when designing synchronous counters, it's in your truth table, we often will do it this way. We'll talk about our present state. Present state. So if we know the present state, the present Q2, Q1, and Q0, what's the next Q2, Q1, and Q0 that we want? So let's have another column that talks about the next state we're interested in. So our next Q2, Q1, and Q0, when it's 000, should be 001. So effectively everything we have in this state, sorry, I wrote that wrong, 001. Whatever you have here, we're going to transfer over there. So 001 will go to 010, 010 goes to 011, and that way I'll just go ahead and complete the table. 0 and 111. After 111, it cycles back to 000. So this is needed. Now, because we're making use of, I said T flip-flops earlier, I'm sorry, I'm going to make use of D flip-flops. T flip-flops are just simply toggle flip-flops. We need to make use of D flip-flops. We can't use T flip-flops to design a synchronous counter. So if we're making use of D flip-flops, then we need to specify what the inputs to each of the flip-flops is. And that will be, if you want, the output of our truth table. Because remember, when we come up with a truth table, we are trying to analyze this table to determine these parameters, whatever we have on this right-hand side here. So this right-hand side will actually be our D2, D1, and D0, which will be the inputs to the flip-flop. So read this truth table as we're trying to ask the question, what do our D2, D1, and D0 have to be in order for the our developed system, the system of flip-flops, to run through these states in this specific order. So to get your flip-flops to go from 000 to 001, your inputs should obviously have to be 001, because whatever is at the D flip-flop input, it gets transmitted to the output. So we could just simply fill this out with this second column. Effectively is what you will have in this right hand side. That exactly is what you have on this right hand side. So let's go ahead, fill this up. 110, 111, and then 000. So these are the various inputs we need to make the counter go from this present state into the next state. So far, so good. Now we need to determine what our D2, D1, and D0 are. And we can go ahead and use our K-maps to do that. I will not use K-maps in this video because you don't always have to use K-maps. Don't take K-maps as a silver bullet that you can use for everything. I mean, they're fine. They work very, very well. But they could possibly be a waste of time if you could analyze the system yourself. So for example, take a look at this system. This is the, if you look at, this is the output at present. This is the next input we want to be at the flip-flop. So to cause the counter to move to the next state, we are interested in. So this is the present output, this is the input. So is there a way, the way we're looking at this truth table is, what is the combination, what's the logic combination we can use, we can have of this output that will result in this particular input? if we can have a logic combination of these outputs that results in this set of inputs, then whenever we're in this state, it will definitely go to this next state, because that logic combination of this particular set of values. I do apologize, there's some noise in my background. That the combination of this logic set of values will cause the flip-flop to move to this particular next state. So analyzing this present state, look at Q2, Q1, Q0, look at D2, D1, D0. Particularly, let's look at D0. Look at D0, look at Q2, Q1, Q0. The first thing that should probably jump out at you is that D0 is the exact converse of Q0. So if I write this, D0 is equal to Q0. Okay, let's just write this well. Q0 bar. I think that is straightforward. Whenever Q0 is 0, D0 is 1. Whenever Q0 is 1, D0 is 0. And that makes perfect sense, because your first flip-flop, your LSB, is effectively just a T flip-flop. Okay, so the Q0 bar gets connected to your inputs of that flip-flop, and it will toggle at every point in time. Your LSB will always toggle whenever there's an active clock transition for this counter. That is perfectly fine. For our next significant bit, D1, we could look at that, and that is a little more tricky to analyze without using a K-map. However, if you take a look at it, notice you have 0 in the first column, then you have 1, 1, and then you have a 0. Every time we have a 1 here, that occurs when you have, initially your Q2 is 0 when we get the 1s. The next set of times we get 1s in your D1 is when your Q2 are 1s. So your Q2 is kind of, the value of Q2 does not determine your D1. So we should look at Q1 and Q0. Q1 and Q0. Notice that when you have 0, 1, you have 1. When you have 1, 0, you have a 1. When you have 0, 0, you have a 0. When you have 1, 1, you have a 0. Let's check that again. 0, 0 gives us a 0. 0, 1 gives us a 1. 1, 0 gives us a 1. And 1, 1 gives us a 0. So this looks like there's an XOR relationship between our Q1 and our Q0. So I'll simply have this as Q1 XOR Q0. And now we come to D2. Now D2 is admittedly is the trickiest to analyze without using K-map. So please feel free to use a K-map for this. However, we can look at our D2. And to look at our D2, we're interested in this particular 4 states, because that is where our D2 is 1. Those are the states where our D2 is 1. However, whatever we come up with for this particular 4 states, we have to reference the other states to be sure that it actually works. So if we say that, okay, we find a pattern here, if it also works there, then it means that pattern is invalid, because for those states, D2 is 0. So D2 is 1 for these 4 states. And first of all, I'll highlight these 2 states. Okay, so let me take off the square. First of all, I'll highlight these 2 states here. Take note that in these 2 states, you have 1, 0, Q2 and Q0. You have 1, 0, 1, 0. And in both cases, and then you have Q1 being 0 and Q1 being 1. So it seems like whenever you have Q2 being 1 and Q0 being 0, then you definitely have a 1 on D2. Let's check. Do we find that pattern anywhere else? No, we don't find that pattern anywhere else. So we are happy with that. We can say Q2, Q0 bar will definitely result in a D2 being 1. Is there anything else? Yes, because we still have 2 other rows to look at. So definitely whenever you have a Q2 Q0 bar, irrelevant of the value of Q1 being irrelevant, so irrespective of Q1, whenever you have Q2 Q0 bar, definitely your D2 will be true, will be 1. So we have 2 states sorted out. We have 2 states left to go. So sorry about that. Okay, so now we want to look at these other 2 states, state 1 and state 2. Do we find a pattern there? Yes, it seems like there is a pattern. For one thing, your Q0 is definitely 1. So for the other 2 states, your Q0 is definitely 1. Okay, so your Q0 is definitely 1. And then what else do we see? We see an XOR relationship between Q2 and Q1. So is there any other state where you have your Q0 being definitely 1 and you have an XOR relationship between Q2 and Q1? Let's check that out. When Q0 is 0, this gives, you have 0, 0 here, so that definitely gives us a 0 if we have an XOR between Q2 and Q1. Where else? Here also, you have your Q naught being 1, and you have 1, 1 for Q2, Q1. This also will give us 0. So this works perfectly well for us. So we know that we have a Q not being true, and we have an XOR relationship between Q2 and Q1. And we're done. We've come up with the expressions for D naught, D1, and D2. So now we can draw our synchronous counter. It's a 3-bit synchronous counter, so we're going to need 3 D flip-flops. So this is first flip-flop here, second flip-flop, and the third flip-flop. Now, to try not to make this diagram messy, I will not put the entire circuitry together. I may have to split the circuits a bit. Sorry, I'm writing DA. This should be D. So because we're used to reading things MSB first and then LSB last, I'll put my D2 here, and this will be D, if I can write, D1 and my D naught. Each of them will have a clock input, and each of them will have a Q output. So this first output here will be Q2, this output will be Q1, and this output over here will be Q naught. Good. So we have this here. Now, because it's a synchronous counter, you will have a clock signal that will go to each one of these flip-flops. The same clock will go to each flip-flop, and that is why we call it a synchronous counter. Each one of them gets clocked at exactly the same time. Now, all that we have left to do here is to put in our circuitry for D2, D1, and D naught. D naught is the easiest to do, so let's start from there. We need a naught, okay, so I'll leave out the naught. Instead, I'll just put a bubble here, since we can use that for inverting the signal. So we know that we are our Q naught. We said D naught is equal to Q naught bar. So we invert our Q naught signal, and we send it into D naught, and we're perfectly fine. So put a bubble at D naught to show that we are inverting our Q naught. First flip-flop done. Second flip-flop, we need an XOR between Q1 and Q naught. So we need an XOR gate. I'll try to draw one here without things getting too messy. So I need one signal coming from Q1, and I'll take the second signal to just try to keep things relatively neat. I'll bring it around this way. I do apologize, things can get quite messy very quickly. So we have an XOR between Q naught and Q1. That comes into your D1. D2, what will go in there is this particular circuitry. Now, it will be a little complex to draw, so what I'll do is, well, I have two options. One option is just to tell you that, okay, that is what it is there. I don't have to draw the circuitry, or I could scroll down and draw the circuitry. I think I'll just leave it like this, since ultimately what we want to do is go and define this in VHDL. The circuitry itself is not our priority. So I'll just leave the circuitry this way, and just take note that what you need to do for your D is, if you permit me, I'll just leave it this way. I just simply say this particular equation, connect it into your D2. So this is what you're supposed to connect into your D2, and your circuitry is done. Once we have this, it should work correctly. So let's go into VHDL. We'll write the code for this synchronous counter, and if we've done everything correctly, then when we run this, when we simulate it in a test bench, we should see it counting through this sequence. So we open up Quartus, new project wizard, and I'm going to create a new project for a synchronous counter. Next, we'll walk inside counters, and then I'll call this S counter, or let me say sync counter 1, because I intend to have another synchronous counter that we'll define. So sync counter 1, that's a folder that I'm creating for that. I'll just copy this name, sync counter 1, and I'll make that the name of our project and the name of our top level entity. So it will be inside that folder. It doesn't exist. Do I want to create it? Yes. Do I want to add anything in here? I could bring in my definition of the T flip-flop in here, I'm not sure we quite need it, so I'll just leave this for now, and if we decide to use it later on, then we'll bring it in. For now, 10M 50 DAF C, sorry, there's a space here, 10M 50 DAF 484C7G. That's the name of our device. And we have simulation is model sim altera, doing this in VHDL because we're going to use a we're going to have a test bench, so I'll go ahead and have this here. Now, like I mentioned in the previous video, we could just do all of this within model sim since we're just writing a VHDL code and we're going to test it in a test bench. So we honestly do not need to do this in quarters. We could have just done all of this in model sim, arguably to be a little faster because we don't have to create a project. We can just create a VHDL file, simulate it. However, I'm doing this in quarters because ultimately I'm going to end up programming a synchronous counter that we develop on the DA10 light board and see it actually operate on a physical board. So Control N, new VHDL file, and let's go ahead and create our code. Library IEEE use IEEE standard logic _1164.all, and then we'll have our entity. I believe I still have it, yes. Sync counter 1 is and entity sync counter 1 ports, close that. Now, what do we need as our ports? We know that we need three. Okay, so what we're going to need in here, let's just pause, and we haven't done our design very well yet. So we've not talked about the design. All we've done is do some basic of design. I'll just save this first of all, and let's come back to our design that we have over here. Now let's plan out our circuits. We know based on what we have done here, we need to have D flip-flops. Okay, we need to have D flip-flops, and we'll bring in, if we bring in D flip-flops, then we can make use of them. Now what I'm going to do is create another entity below for D flip-flop. So okay, so because I have sync counter, let me just put this first of all, architecture count of this is okay. So I just wanted to have, since I still had that in my clipboard, I wanted to use sync counter here and architecture counts. Okay, good. So let me create a new entity called D flip-flop. So new entity called D flip-flop. I believe DFF is a keyword, so I'll call it my underscore DFF. Okay, and end entity my DFF. Now, like we did with our T flip-flop, we could define our D counter to have asynchronous set and clear. I wouldn't do that in this particular case, or okay, I'll go ahead and do that in this case as well, so that we have a D flip-flop that definitely can do everything we want it to do. So ports, and I'll probably just speed things up here because you already know how to create the D flip-flop entity and create this architecture. So I'll just speed this part up. Yeah, let that run through. I just want to be sure that the D flip-flop has no error in it while we're comparison. We could focus just on the synchronous counter. Okay, so while that is going on, let's come back to our design and now ask a number of questions. So we're going to need some signals here. Now, these are things we should obviously have specified at the very start, but we're going to need to have some signals over here, and it will just make a lot of sense to have each of these being a signal. So I'll say S underscore D2. I'll connect a signal to each of the inputs. I'll connect a signal to each of these outputs. So S underscore Q2, and I'll do that for each one of them. Same thing for our presets and our resets. I'll do I need signals for those? No, I really don't need signals for those. But we have our preset and our clear. Well, set N and clear N. I don't think I need signals for that. I think I'll just leave those without signals. So let's go ahead and create signals. So we need a number of signals. Signal, I need to have S underscore D1. Well, let's start from D0. S underscore D1, S underscore D2, S underscore Q0. So I'm going to do a port mapping, and I'm going to have to have three components, three D flip-flops in there. So I'll call them my underscore DFF0, my underscore DFF1, and my underscore DFF2. I'm going to the component I'm bringing in is DFF, and I'm going to do a port mapping. Because it could be more convenient to do so, I'll do this in a number of lines. I won't do them all on the same line. Now I need to map CLK to, okay, I don't have a signal for the clock. Do I need a signal for the clock? I don't need a signal for the clock, I believe. So CLK can just go directly to the clock. Since all of them are connected to the clock, I'm not doing anything else with the clock. That should be fine. Then we have to my D. Okay, so my D of the no, by the way, VHDL is not case sensitive, but I always like to be consistent with whatever cases I'm using over there. So you see me changing lowercase or uppercase. That's just because I like to be consistent, not because VHDL is case sensitive. The one case where you could run into an issue when using quarters is in your QSF file. Your QSF file actually is case sensitive, so that if you have a port defined as lowercase d in your VHDL code, in your QSF file, in your specification file, you have to, when you're doing your pin assignment, you have to specify it as lowercase d, or quarters may not be able to do that pin assignment correctly. Now, what are we connecting our D not to? So this is D of our LSB. If you remember from your diagram, it is Q not. Okay, so this will be not S underscore Q not. Now, model sim will, when we're doing our simulation in model sim, it will have a problem with this. So I'm not going to do this assignment. Instead, what I'm going to do is to create this. Now, I can do this before, I can do this after the port mapping. These are concurrent statements, so the order in which I do it does not really matter. So I'll do SD underscore 0, and we're going to assign not S underscore Q not to that. My S underscore D1, I'm going to assign, I think it is Q1 XOR Q naught. Yes, Q1 XOR Q naught. So I'm going to assign that Q1 XOR S underscore, I need to make that S underscore Q naught. Q naught. So this should be S underscore Q1 and S underscore Q naught. Good. So I have that XOR. And finally, S underscore D2. I'm going to assign S underscore, what we have there is Q2 Q naught bar, and then we have this. Let's take that one at a time. Q2 and S underscore, sorry, and not S underscore Q naught. This should be Q2. Q2 and not S underscore Q naught. I'll put that in parentheses, or, and and then the rest will be also be in parentheses. I believe it is Q. Well, let's just make sure we're not making a mistake. This is Q naught and Q2 or X or Q1. So we have S Q naught or sorry and S underscore Q2 X or S underscore Q1, and we're done. I believe I've closed all the parentheses, so that is that. So now I can just simply connect my S underscore D1 signal to my D1, and model sim will be perfectly happy with me. Next, I'm going to take my set N. So this is a set N for the LSB flip-flop. So I'm going to take my set N signal. Remember, we have an input here that is set N. So I'm mapping this set N to the LSB of this set N. So I'm going to take this, and I hope model sim has no problem with this. And then I'll map my clear N of this particular flip-flop to the clear N LSB of the entire entity. You might ask the question, how does Quartus or model sim, or I don't use the word VHDL because VHDL is just the language, how does the compiler know which is which? Now, when you're doing a port mapping, the left-hand side is a member of the component. The right-hand side is what you're mapping it to. So the right-hand side is not a property of the component. The right-hand side is a property of the entity that is calling, that is within which this port mapping is going on. So that is how the compiler knows which is which. And finally, we have our Q that we're mapping to S underscore Q naught. Okay, and this is the port mapping for the first. This is fine. I'm going to copy this and paste it below to save some trouble, to save some time. So for my DFF1 and my DFF2, I will just need to change this to, okay, so this was wrong. This should have been SD0. Okay, so this SD1 is now SD2. A comma is missing. Comma is missing at the end of each one of these. Comma, 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 comma. Okay. Then I need to change this. It's no longer the LSB. Now it will be the first bit, and here will be the second bit. This needs to be Q2. This needs to be Q1. So I think we're about done with the port mapping, and this should be perfectly well, except that there's one more thing we have not done, and that is my output of the entity. Output of the entity is S underscore Q2 ampersand S underscore Q1 ampersand S underscore Q naught. Now remember, this is a concurrent statement with the port mapping. They happen at exactly the same time. The order in which you do this is entirely irrelevant. Just to make things a little clearer, I will put one extra empty line between those. I'll tell this to compile this, and I'll just take a look at it one more time to just make sure that I have done everything I think I should do. If this is fine, then we'll go ahead and create a test bench. We'll go ahead and create a test bench and see that all is fine. So Control N, I'll create a test bench, a new VHDL file, and I'll just simply call this test bench, so that this is a test bench I will use for any other systems, any other entity I will create. So I'll just simply call it, okay, library IEEE, use IEEE dot standard logic 1164.all. I'll simply call it test bench, and I'll just use this test bench for any other test I want to do. NNCT test bench. So what I will do is, in future videos, when I want to test a different circuit in a different entity, I'll just have a new architecture, but I don't have to delete this former architecture. So architecture tests sync counter 1. So I know what I'm testing of test bench is. Okay, so our compilation occurred, went through successfully, thankfully. architecture, if I can type, test sync counter 1. This is to be off. I'll need a number of signals. Specifically, the number of signals I need is dependent on the number of ports that I have here. So I'll just copy this and paste it in my code here so I don't have to keep on referring to that. So I'm going to need signal tools, run simulation tool, RTL simulation. Oh, okay. While that is opening up, let's expand analysis and synthesis. Go to Netlist Viewers, RTL Viewer. Let's open that up as well and take a look at what that looks like. So this is the RTL Viewer. Model sim will open up in the background shortly. But this is the RTL Viewer. Take note, it uses 3 components. Each of those components is my DFF. Let's expand one of them to see. My DFF makes use of a D flip-flop, and you have, as we expect, it's a preset and a clear. We've seen something similar to this, so we won't bother trying to walk through this circuitry right now. Then, this is what we defined over here. So our clock signal goes to each one of the inputs, like you can see. Clock signal goes to each one of these components. Where's our LSB? This is the LSB over here. This component is the LSB. Look at our D input, and the D inputs is our okay, so it's just simply wired to the output. But then notice that this, what you have is a thick wire over here, and this wire here that goes into your D flip-flop is thinner. It's significantly thinner because it's just taking one of them. You have your bubble here saying it is inverting that signal. So if you just look at this and you see that apparently it is doing exactly what we told it to do. You have your XOR gates over there, you have your AND gates, OR gates, and so it's doing exactly what we told it to do, and that is fine. Model sim is open. Just to check, if you check in here inside our work folder, you have the my DFF, which makes sense. It created that. You have your sync counter. Take note, you do not have test bench in here. because that is not a child of it. So it's compiled, but it's not inside your work folder. So let's go ahead and just compile that particular file. So I've clicked on the compile button, and let's look for the VHDL file we're interested in. The specific VHDL file we are interested in is, let's go up, test bench, compile. Compiles 0 errors, it's happy with us. Now we have it in our work library, and we can simulate the architecture we are interested in. Okay, now these are our various signals we're interested in. So we have S clock. Just going to add all of these to, it seems to still be doing something. It's not yet responding to me. What's going on? Loading. Okay, I guess it's probably still loading something because it's not responding to me just yet. Okay, so here it is, and I'll just select all these signals and add to wave. Now, something I just want to point out here is in our test bench, my clock, set n, and clear n are input signals. We initialize them. You see the values here. Those are the values we initialize them to. Take note of our SQ is unassigned. Okay, is unassigned. It was an output signal. Let's go back to quarters and see. Didn't we initialize it? Our SQ was initialized, but because it is taking its output from an entity, even though we did this initialization, as far as the compiler is concerned, actually it is uninitialized. It is on, as at now, it has not yet been given a value because it takes its value from the entity, not from our initialization. So take note that all those initializations you do in signals may not necessarily translate into reality. It will ignore whatever it needs to ignore, particularly those that come at the output of entities. So we can go ahead and run this. I'll run this for, say, 50 nanoseconds. I'll run it, right click on this, full, and we see our system over here. I'll pop this out and make it larger. Pop it out, make it larger so that we can hopefully see it better. I do apologize, there's a dog barking in the background. Hope you can still hear me well. Now you could always click on this plus sign beside the counter to look at the individual signal. So that's our set n. Okay, so I think I need to run this for a little longer in order to be able to see more. Yeah, so we have our set and we have our clear at some point in time. So we could run through this with our code. What we did was initially we made our clear signal active. So we cleared each one of the flip-flops at this point. Now, nothing changed in our output at that point. Okay, so things were uninitialized before then, but when we cleared, now our output was forced to 0. So it is always a good idea. This shows us it's always a good idea to clear before you start any counting sequence. If we had tried to start a counting sequence without clearing initially, I'm not entirely certain what would have happened. Actually, we could try that in the code right now and see that. I'll try that shortly. But taking a look at this, we see we initially cleared, everything went to 0, 0, 0. Now, in an earlier video, I mentioned radix when I talked about test benches. Let's right click on this and let me change the radix to decimal. Okay, I change the radix to decimal. Now you see the values in decimal. Okay, now it is treating this as a signed number. Let's check. Okay, so I made it decimal. Now let me make it unsigned. If I make it unsigned, now it treats it as an unsigned number. So you have 0, 1, 2, 3, 4, 5, 6, 7, back to 0, 1, 2, 3. And then at this point, we now introduced our set signal. Okay, so at this point, we now our asynchronous set preset was done. So it forced it set all the flip-flops. In setting all the flip-flops, note the value is 7. It sets all of them, it makes all of them high. Okay, if I expand this, you see it makes all of them high. So the value there is 7, and then it starts the counter again, 0, 1, 2, 3, 4, 5, 6, 7, and it goes on that way. So we see our D flip-flop is working fine, and our synchronous counter is working exactly as designed. And we've seen that you could also use your radix. We use decimal, we use unsigned. We could go back to global setting and it goes back to binary, or we could say we want it specifically to be hexadecimal if you want, and this is the value in hexadecimal. Is the same as decimal in this case because we never exceed 9, so it looks the same as what you have as an unsigned number. So this is our circuit. Now I mentioned that we could change something in our design. Let's go ahead and change that here. Let's say we did not clear. Where did we clear? We did our clearing here. So let's comment these lines out. Toggle comment. So let's comment those lines out, and let's go ahead and compile this once again. And so done. I'll close this. I'll end this simulation. End simulation, and I'll compile. I do apologize for that. It has moved my model sim window away from the screen. I just bring it back in here. So I'll compile that the test bench once again, since I've changed that, and then run this simulation one more time. Okay, so we have these signals I want to add to my wave, and then this is my wave that I popped out a little earlier. Now it's back open, and let's go ahead and run this for, I'll run it for 80 nanoseconds this time. Run, make this full, and see what happens when we didn't start by clearing. It is uninitialized up until the point when we force the signal to go to 1, because if you have an uninitialized signal, if it does not know what the logic signal is, then when you have this tell you, say not of Q naught, for example, not of an unknown signal is an unknown signal. An unknown signal X or an unknown signal is an unknown signal. So you always want to clear or set, or at least make sure you force your counter into a state you are sure of before you start using it. Take note about that. That's one thing that has shown up from this simulation. So I'll stop this video at this point, and in the next video, we're going to this same counter, we're going to design it in VHDL using a different method. See you in the next video.